Have you ever really stopped to think about those invisible shields that protect so many things we use every single day? You know, the chrome on a car, the special finish on your tools. Well, those are electroplated coatings, and they are some serious engineering marvels. Today, we're going to pull back the curtain and uncover the incredible science that makes them work.
I mean, we've all been there, right? You buy a shiny new tool, and it's a rusty mess after one season. Or you see that chrome bumper on a car starting to peel away. The difference between a coating that just gives up and one that lasts for ages, it all comes down to the science. So today, we're going to put these coatings through a scientific gauntlet to find out what it really takes to survive.
All right, so here's our game plan. First, we're going to get a handle on what these shields are all about. Then, we're throwing 3 major challenges at them. Think of it as a trial by fire. We're testing adhesion, chemical attack, and pure physical strength. And finally, we'll see how it all comes together to build a truly superior barrier. Let's get into it.
So at its core, electroplating is this super precise process where engineers lay down a microscopic layer of metal onto a surface. It's like creating a custom-fit suit of armor. But, just making the shield isn't enough. To prove it's actually any good, it has to pass a whole battery of really tough tests. And those are the exact challenges that make up our gauntlet today.
First up in the gauntlet is maybe the most fundamental challenge of all, adhesion. I mean, it sounds so simple, right? But if a coating can't form an incredibly strong bond with the surface it's supposed to be protecting, well, everything else is totally pointless. So the big question is, how do scientists actually make it stick? Well, the secret, it lies in this amazing concept called morphology. We're talking about the shape, the form, the texture of the coating at a level so small you'd need a crazy powerful microscope just to see it. You can think of it like the foundation of a house. If the shape isn't right from the very beginning, the whole structure is just bound to be weak.
Okay, so this breaks it down perfectly. You'd think a super smooth surface would be ideal, but look at the left. It's actually terrible for adhesion. There's just nothing for the coating to grab onto. So what do engineers do? The exact opposite. On the right, they create something called hierarchical texturing, which is just a fancy way of saying they rough up the surface on a microscopic scale. This creates a physical grip, kind of like microscopic Velcro, that literally locks the coating into place.
So let's look at a real-world example. Here's the standard nickel phosphorus coating, or NIP for short. It has a really distinct morphology. Under the microscope, it looks kind of lumpy, almost like a cauliflower. And while it does offer some protection, all those lumps and gaps can become serious weak points, which can lead to peeling when the material gets stressed out.
But now, watch what happens when scientists make one tiny change. They just add a little copper into the mix, creating a NiPCU coating. And this right here shows the incredible power of morphology. The entire structure transforms from that lumpy cauliflower into this dense, beautiful pattern of tiny, tightly packed spheres. And believe me, this new shape is going to be a total game changer for the rest of our tests.
Okay, our coating passed the first test. It's stuck on there good and tight. But now it's got to face its next opponent, the environment itself. This challenge is all about fighting corrosion, or as we all know it, rust. A truly great coating has to be a perfect, impenetrable barrier against any kind of chemical attack.
Now, to measure how well a coating fights corrosion, scientists use a test called potentiodynamic polarization. Yeah, it sounds super complex, but what it's really doing is creating a highly controlled way to speed up the rusting process. The test gives us one crucial number, the corrosion current, or I-core. And all you need to remember is this. For this test, a lower number is way, way better.
So, how did our 2 coatings do? Well, this table makes it crystal clear. The standard NiP coating, our cauliflower, it has a higher I-core value. That means it has lower resistance to corrosion. But just look at the NiPCU coating. Its corrosion current is significantly lower. That dense spherical morphology we talked about, it's creating a much, much tighter seal. It is the undisputed winner here. And scientists can dig even deeper with another cool test called electrochemical impedance spectroscopy, or EIS. Honestly, the best way to think about this one is like an alarm system for the coating's armor. It sends these tiny electrical signals through the material, and if there are any invisible cracks or tiny defects, this test will find them long before they become a real problem.
Our coating has survived the gauntlet so far. It sticks tight and it resists rust. But now comes the final, most brutal challenge, physical strength. How does it hold up against the daily grind of scratches, friction, and impacts? This is the real test of its durability.
And to really understand the results of this final test, we have to go all the way back to the beginning. Remember those two different morphologies? You had the lumpy cauliflower structure versus the dense, tightly packed spheres of the Naipiku. Well, that tiny difference in shape is about to pay off in a huge way.
So when scientists measured the surface hardness, the NiPCU coating wasn't just a little bit better, it was more than 8 times stronger. Just let that sink in. 8 times. That's not an improvement, that's a revolution. And it's all thanks to changing the coating's microscopic shape.
So, why such a massive difference? It all comes back to that superior morphology. First, that denser structure means there are way fewer gaps or weak points. Second, the grains themselves are smaller and tighter, which creates a stronger internal structure. And, most importantly, when you apply force, those little spheres distribute the load evenly, which prevents cracks before they can even think about starting.
So, we have made it through the gauntlet, and the biggest thing we've learned is that a high-performance coating isn't just one thing. It's not just about being sticky, or rust-proof or hard. It's about how all of those properties work together, in concert, as a single integrated system. So really, a coating's performance rests on 3 essential pillars. First, adhesion. It absolutely has to stick, and that's where morphology is king. Second, corrosion resistance. It must be a perfect seal against the elements. And third, hardness. It's got to survive physical abuse. And here's the kicker. If any one of these pillars fails, the whole system comes crashing down.
This quote from the research really just says it all. Morphology and adhesion considerations are inseparable in electroplating system design. What that really means, in simple terms, is that the structure is the strength. The shape of the coating at the micro level determines everything else.
And this stuff matters far beyond our cars and our tools. By understanding and mastering this science, by putting materials through this exact gauntlet, engineers can design custom coatings for the most demanding jobs you can imagine. We're talking about things like biocompatible medical implants, or components for spacecraft that have to survive the insane conditions of outer space.
So we've gone from just, slapping a layer of paint on something to truly engineering its structure at a near atomic level. And it leaves us with a pretty fascinating question for the future. As our control over materials gets more and more precise, what's the next unbreakable surface we're going to create?